I'm Scott Peckham. I'm a research scientist at the University of Colorado, and I'm a soft money scientist, so that means I end up working on all kinds of different things as the money appears. And one of the things I worked on for about 7 years, which is an NSF-funded project called CSDMS, which I'm going to talk about a little bit first. And that's where I really started to focus on cyber infrastructure issues and looking into what's going on in that realm. And then now I'm funded on some NSF EarthCube projects. And so I'll talk a little bit about that if I don't get too wordy in the first part of the talk. So I can't, the arrows don't advance it. This is not advancing it like that. There we go. Okay, so this first segment will be about the Community Surface Dynamics Modeling System, or easy to say, CSDMS. And this is our this is our wiki website for that project. It's pretty elaborate. CSDMS is sort of two things. It's a model inventory of models that are out there, but then it became more and more about being able to prepare those models for plug-and-play reusability. And part of the website is this list of models by categories. So there's terrestrial models, coastal models, ocean models, hydrologic models, so lots of different categories there that you can browse. And these are all open source models developed mostly by academics, but some of them are very sophisticated. Some of them are used operationally. And we have this project, it's in its second 5-year funding block right now, and it has over almost 1,300 members, which are people that just said they wanted to be a member and join this effort, scattered around the world. And they have annual meetings and they have working groups that focus on these different types of models, terrestrial, ocean, coastal, and then some focus research groups, including a Chesapeake Bay focus group and a hydrology group and some other groups. And so it's had a pretty big impact. And we've had some successes that that were hard-won successes. So I sort of want to share with you what we struggled with and what we finally ended up with as a solution. But before I do that, one of the things that is a barrier to communication with this is there's so many overloaded terms with this kind of stuff. So I like to have a little slide where I talk about what I mean when I say model or modeling framework or whatever. And I'll try to keep it short because it's easy to spend a lot of time on this slide. But when I'm thinking of a model, I'm thinking of a computational or numerical model that has some kind of state variables that describe some system. And then often it's discretized in space, it has a geographic context, and uses laws of physics to march this thing forward in time until it gets state variable predictions at some future time, and they're shared. So it could be a climate model that wants to predict future climate, or it could be a fish growth model that predicts how big the fish are going to get after a couple years in this lake. Whatever it is, there's some variables that that are of interest, and they're being advanced in time, and often with a grid. A model component now is something a little different, where it's been prepared somehow by some process to be more plug and playable, and to cover over its heterogeneity, to make it look more like things that can be reused with others like it. Then an interface, another very overloaded term, but in computer science, an interface is, you think of like an API, not a GUI, not a graphical user interface, but it's a standardized set of function which some caller uses to interact with your resource, whether it's a model or data set or web service or whatever it is. And standardized interfaces are really the name of the game nowadays with interoperability in EarthCube and in lots of the projects that are shooting for interoperability. Then you have this class of software called modeling frameworks, and they're popping up all over the world, and they're environments or container software where you can pull down from a palette of known models and connect them so that some of them have inputs others need, and you connect them and make a reusable, a composite model out of these reusable pieces. And they're pretty sophisticated. Some of them are on HPC systems using multiple processors. Some of them are not, but there's a variety of those that are out there, and they're doing great things. CSDMS is one of them. And we're all communicating with each other, so we're not working in isolation. I'm good friends with most of the developers of these other frameworks that are out there. And workflow I won't talk about because I don't really have time. So, so when you have a bunch of heterogeneous resources, you have all these models out there written by different authors, in different languages, different grids, all kinds of things, it makes it hard to link them together, couple them, and that's really what makes it hard. And so we've identified these sort of 5 main ways that the models can differ, which we can do something about. And there's a programming language, but there's a multi-compiling compiler that lets you compile in a way that you have language bindings to call a piece of code from any of these other languages that it supports, called Babel, that was developed by the DOE, and we used that. There's a regridder, an ESMF regridder from the Earth System Modeling Framework, another framework project, that does a great job of converting values on one grid to values on a different grid, and no need to reinvent that wheel. Then there's a time stepping scheme issue where you might have different fixed time steps, or you might have one model has an adaptive time step, and different variable names and different variable units. And so there were off-the-shelf solutions for some of these problems, but not for the variable names thing. And so we've made some advances on this of our own and used other things whenever we could. Now, just briefly, Babel, as I mentioned, it has this way of describing the interface of a piece of code with scientific interface definition language in this hub. And then once that's been done for models written in these languages, they can be compiled so that they can make function calls across that boundary and share variables between something that was originally written in Fortran or C++ or whatever. So we're not converting the code. We never want to take code that's already written in one language and convert it to some other language. That's not what this does. It just makes it so that you can actually pass the variables with the necessary language bindings to make them connect. And it's kind of technical, but it's a great tool. And then there's the regridding I mentioned. This is an example of regridding from one type of grid that a model might have and another type of grid. And there's that ESMF tool for that. Oops. And so one of the things we had to figure out was this standardized interface idea. And we started off really struggling with this in the first part of the CSDMS project. And we were looking what others had done, but nobody had really made it simple. And it was the sort of thing where every model was being treated as something that had to be separately wrapped to make it connect to the framework, which was unsustainable for lots of models. So we hit on this idea eventually called the basic model interface, and it's really taken off. And this is a slide I often use to motivate the idea of a standardized interface. So this unruly crowd here is sort of, but enthusiastic and cheerful. They're a bunch of heterogeneous resources like models that come to CSDMS and get put in our repository. And it's hard to, even though they're great, it's hard to make them work together as part of a single functioning system. And you can imagine they speak different languages, and you might have to use different ways of communicating with each of them to get them to do their thing. If you can do put an interface on them, a standardized interface, you can. We talk about the word wrapper. Well, these guys have wrappers. They have uniforms, and they have. They're still what I always like to point out, because academics really react to this militarization idea. Is that these are still individuals inside these uniforms. You know, they're different races, religions, sexual orientation, whatever. They're still people inside there, just like the models are still models. But now there's a standard set of commands that they all respond to. So if I say about face, or if I say march, take one step forward. If I say halt, they all know that. And that's the same idea with the models. We want to have a command like initialize, update, finalize, get values, something that all the models understand so they can do what I want instead of me having to learn their individual terminology and their individual controls. You can also think of this as kind of like a universal remote for all the devices in your house, you know, so that you don't have to be having a different remote for every single thing you have. And so it's kind of an interesting analogy to think about standardized interfaces. Also, these guys will always know who's in command in a given situation. They have a chain of command, which is another analogy you can pursue here, where they're ranked according to their colors and so forth. So the basic model interface takes a time to explain in detail, so I'll just try to hit the basic idea. The key is to the epiphany that we had eventually after doing this the hard way was that you have these model developers that come to you and they say, here's my model, it's open source, I want to share it with the world. And you don't want to go and give them some huge task back, say, rewrite it in this language or completely rewrite it according to this template or anything like that, because they just won't do it. So you want to have them do something that sort of homogenizes or makes their model a little easier to get a hold of and work with but something that's so minimal that they will do it, something that's so easy and straightforward and seems reasonable that they'll do it, and show them that there's all kinds of added value. Once they do it, they get all this other great benefit on the other side. So there's a social issue as well as a technical issue that has to be simultaneously solved for this to work. And when I was studying all the different modeling frameworks out there, turned out there were certain core things that all the modeling frameworks were requiring the models to do to get to be able to use them in the frameworks. And so this BMI is a distillation of those fundamental things that you will, if you study this, you'll see that these are the things you absolutely need, but they're done in such a way that there's no knowledge of the framework you might deploy in for this. So this is writing some additional functions in your code that you yourself, as the user of the code, wouldn't use, but you make them available to the framework to call. And so there's some model control functions, so you can initialize, update, finalize, like the March about face idea, just 3. And then there's some model information functions and variable information functions. And what all those other information functions are about is making this model self-describing. So it describes itself in terms of what variables it has, what grid it uses, what time-stepping scheme it uses, what the units are for each variable, what the data type is for each variable. It just has functions, so if someone wants to know that stuff, they can call those functions and pull it up. And it follows this idea called in computer science called the Hollywood principle. Don't call us, we'll call you, which means there's no tendrils. There's nothing that you have to import into your code or modify in your code in terms of a dependency or an invasiveness. You're just adding some functions on the outside to say, here's what I'm all about. Here's with standard answers. This is how my grid works, and et cetera. And if you get to that point, if you get your model to this point, which for some people takes a couple hours, for big models it may take longer, it gets you all kinds of benefits. And so what you then are able to do is, this is sort of a schematic of how it works, is 2 modelers get their model ready with BMI, and then there's this one wrapper. These aren't different wrappers now for each model. It's one wrapper that can be applied to either model that converts those functions to the interface that the framework uses, whatever it might be. And then now this thing gets compiled as a plug-and-playable, dynamically linkable unit that a user selects from several of those precompiled units, puts together a model, and then the framework is able to run them as a composite model. And what it does is if this one says I have a variable I need, and this one says I have a variable that I want that's the same one, they tell the framework what units they have it on and what grid they have it on or what grid they want it on, and these service components reconcile or mediate those issues. So if this one has something that one wants, but it's on a different grid, it regrids it to the grid that it wants. If it has different units, it changes units to the units it wants. And so there's time interpolation, and anything that you can imagine that would reconcile these differences between the models takes place here inside the framework. And so you get a plug-and-playable system this way. I keep hitting the wrong advance button here. So I'm going to talk a little bit about model coupling metadata, because that's key to this, and it's actually integrated into that BMI, those interface functions. When you implement those, you have to map to standardized variable names that you might want to exchange between variables. And this is the basic problem that we have on that front, where imagine you have 2 hydrologic models, A and B, and this one has output variables of stream flow and rain rate, and that's the terminology it uses internally for those variables. And then this one has input variables, discharge and precip rate, and that's the terminology it uses. Well, you'd like this framework to be able to automatically see that these could be paired up and they could share those variables, but for us to know that as hydrologists, we have to have domain knowledge. We have to know that there's a bunch of synonyms like stream flow and discharge that we can apply our domain knowledge to. We don't want the framework to have any domain knowledge. It doesn't. So often at these kind of problems, you have a hub and spoke approach. It's very efficient, where you have a very expressive hub that all these individual internal vocabularies can be mapped to and then mapped back out of, so that the framework can match these things up. And it's called semantic mediation or semantic matching. And so we've generated over about the last 3 years a naming convention system for how you would name the variables that appear in models in a standard way according to rules, so that 2 people are likely to name something the same way if they follow the rules. And it has an object part and a double underscore and then a quantity part, and a bunch of nice properties in terms of alphabetization and nestedness of objects, and I don't have time to fully explain it, but it works really nicely for this, and we use it in the CSDMS framework. the pattern is to have an object name, some optional operation, mathematical operation like time integral or time average or something, and then a quantity name. And that operation actually creates a new quantity from the existing quantity. And there's a very extensive set of web pages that talk about this whole system and how it works, and has standardized process names, quantity names, object names, some basic rules, and so forth that you can look at there. There's also assumptions where you're trying to describe not just the variables to be exchanged between models, but the fundamental assumptions a model makes, so that you can see whether two models are compatible from a physics point of view to be coupled. And that's also been, we have 1,000 assumption names now for that purpose, drawn from the way scientists talk to each other. Now, on this last part, I want to talk a little bit about a newer project. I'm no longer working on the CSDMS project because I've gotten totally pulled into this NSF EarthCube effort, which is about 2.5 years in total since it was first initiated. And there's a lot of separate funded projects called Building Blocks. There's projects called Conceptual Design Projects. There's Research Coordination Network. So it's a pretty big program at NSF with a lot of money being put towards cyber infrastructure. And our project is Earth System Bridge. There's our little bridge icon and some of the icons. The icons on this side of the bridge are mostly academic groups, modeling groups that do something like COASI or CIG or CSDMS or these universities. The ones on the other side of the bridge are operational frameworks or federal agencies. And there's a lot of work on this model coupling happening on this side and this side. And Cecilia DeLuca, the first one shown here, she's been leading the ESMF, Earth System Modeling Framework project, for many years and has connections to a lot of federal agencies with NOAA, NASA, a lot of people that use her stuff. And then a lot of the people on the academic side use our stuff. And so we've teamed up now under this EarthCube project to create interoperability between the modeling frameworks so that you can give model developers a target. If they hit that target, like BMI, now they can deploy their model in any of several frameworks with no extra effort on their part. And this is our little website under the, it's part of the Earth System Grid Federation project. And one of the things we did for this effort is to come up with standardized metadata to describe not models, but modeling frameworks. And so ESMF is a big modeling framework, and CSDMS is a big modeling framework, and there's many others. And so now we're saying, well, how do we, if we wanted to understand them all with a rap sheet and understand how they differ, what they can do, can they be grid, can they do different things, we want to have standardized descriptions of those, and it'll help us look for ways to share between them and to coordinate our efforts. So this is one of the things we've done with one of those, with Rocky, who was on that last slide. And then another thing we did was we have projects, we already had the ability to take a BMI model into CSDMS, but now we have separate teams working on a single adapter that will take a BMI model, a BMI-enabled model with that interface, and allow it to be deployed in the ESMF framework or this PIRE framework for deep Earth process work, or the object modeling system of USDA, or this OpenMI effort from Europe. And so we've got showing that this low-level distillation of what modeling frameworks need means that a single little wrapper here for each of these arrows will turn that model into something that can be plugged into that other framework. And so this is another example of interoperability between frameworks and finding what's the essence, what's the common denominator of all these things. Another thing, though, that has to happen there for the interoperability between frameworks is that some of these frameworks already use some kind of standard vocabulary of their own. So then you need crosswalks from something like the COASI variable name control vocabulary or the CF climate and forecasting convention names that are used in the ocean atmosphere community and also by ESMF somewhat. You need mappings between those, and so we're also working on that part of it so that these mappings can be inside the framework and automatically reconcile not just model to hub, but also between two standards for doing this. And then we've got a couple of demonstration projects that one of them is focused on ESMF capabilities, one's on CSDMS, where we're taking models at different scales meant for different purposes and showing that these tools can actually allow them to be easily interoperable. And so my last slide, I don't know, how am I doing on time? Am I okay? My last slide is just some list of some papers, and I figure these these talks will be shared somewhere on the internet, so I've embedded references here, and I've also embedded URLs throughout the talk that you could follow if you download the PDF. And that's it. So thank you.
Okay, I compensate, I guess, Scott for the introduction, so perhaps we have time for one question for Scott, and we can follow up in the break, of course. Jay? The microphone.
To what degree do we all have to become computer scientists to do this work? Versus how do we, I mean, the hard part, I think, to manage these big integrated modeling projects is the expertise for each of the modeling components and the computer science expertise needed to sew it all together and keep your mind straight in terms of the data are all bigger than your own head. So how do you recommend, what are your thoughts on how we might do that better?
Well, I mean, the idea here is that you definitely don't have to be a computer scientist. We've made this very low bar, which is this basic model interface that we've tried out on our community, and we got buy-in. They said, "Oh, that's easy. I can do that. I can write some functions to describe my model," and what we did initially in the first 2 or 3 years wasn't that, and so we got a lot of pushback. I'm not doing that to my model, you know. And so we found this sweet spot where they'll do a certain amount. And that turns out to be just what we need from them. And so now we're able to spread that work out. But the computer science magic happens now that the framework developers have that to work with. They can really work their magic, and there can be easy to maintain sets of code that will then interact with all of that stuff. And so this is really pulling in computer science concepts to make the modeler's job just as easy as we possibly can make it. And that's what EarthCube is really trying to do too, is trying to, across the geosciences, take these successful projects like CSDMS and Kwasi and all these things and get them to start to be interoperable between themselves. Because right now they're maybe bigger than a silo because they're spreading, but they're not big enough to be spanning the whole U.S. yet. And so there's sort of like a gelling process where things are getting house is getting tidied up over here and over here and over here, but they haven't all kind of like connected into one functional unit, and that's really what EarthCube is trying to do.
Thank you very much.
Sure.
Thank you very much, Scott.
Thank you.